for this. So good morning. Welcome to one more colloquia talk from the Athena European University and International Relations Office of the Hellenic Mediterranean University colloquia talk. It's a great pleasure to have today with us one of the most distinguished scientists in his topic, Professor Ferrari. I will provide a short introduction about Professor Ferrari. So he has earned a PhD in electrical engineering from the University of Cambridge. He's a professor of nanotechnology in the University of Cambridge, professional fellow of Bembrough College, and he has founded the Cambridge Graphene Center. He chairs the management panel and is the STO, the Scientific Technology Officer of the European Graphene Flagship. He is a fellow of American Physical Society, Materials Research Society, and Institute of Physics. He has received 4 ERC grants. His work has received more than 146 citations, and his H index is 126. The today's talks from Professor Ferrari is entitled Layered Materials, Characterization and Applications. So, as I said, Professor Ferrari, it's a great honor for our university to have you with us, and the floor is yours. Thank you very much.
Much for your introduction. Yeah, I have a bit more than 146 citations, but
I mentioned 146,000. I'm sorry.
Okay.
Yeah.
So, and I can try to share the screen now. So let's hope everything works fine. So we share the presentation. Optimize for sound. Sharing. Okay, hopefully you can see it.
Yes, very clear. Thank you.
Thank you. A full screen. Yes.
Correct.
Okay, so I can see you as well. So we are all set. Okay, so thank you very much for the invitation to give this lecture. And I will keep it a bit general, and I will not discuss about solar because there are plenty of experts there. So I will keep clear of this aspect. So what I want to do in the next 40 minutes or so is some people want to get in, cover some topics. In particular, I want to discuss about the large-scale production of layered materials. I will then give some examples of how these are used, and then I will want to focus my second part of the lecture on the optical properties and on the modulators, detectors, and lasers, and then I want to finish on the quantum devices. I probably don't have enough time to go through all of this, but hopefully I can show you the breadth of application. And as I said, I'm not going to be able to cover all of what is possible with layered materials. I just made a selection. And in particular, in the central part of the talk, I will try to discuss some interesting application for biology. Okay, so we really need to remember where we started from. In 2004, this was a piece of graphene. It was 1 micron. This is an actual real picture of 2004. It's either something we did in Cambridge or it was done in Manchester. I don't remember at the time. We started working in graphene more or less at this time as well. But what happened is that just in 6 years, by 2010, thanks to the work of SKKU and the work of Rod Ruoff and Luigi Colombo the year before in 2009, in 2009, a graphene flake of 1 centimeter square was made, and by 2010, 30-inch were produced. So this was really a massive step in large-scale production happening only in the space of 6 years. And nowadays, graphene can be produced at large area, and let me speak about the sort of Cambridge experience. Around 2001, Ken Teo was a lecturer. He was a student, a PhD student in our department, 2000-2001, together with Manish Chawala and myself. We were all finishing our PhD at the time, and Ken took a second-hand evaporator and turned it into a system to grow carbon nanotubes, and this was published in Journal Applied Physics in 2001 to grow aligned nanotubes over a large area. Then Ken started his own company, and then the company was sold to Einstein, and he moved to Einstein. And when Graphene started, he modified the original nanotube system to create what is now called the BM Pro. In fact, this is out of production now, and is a lab scale 4 to 6 inch system to make graphene. So that was pretty quick because it was just a modification of the original nanotube system. And already 3 or 4 years ago, these systems were scaled up to the BM300T and the Neutron. They were able to produce wafer scale 200 to 300 millimeters and continuous production of graphene. So this is an example of the Neutron natural system. So the graphene goes up, the roll goes up from the top, goes inside the chamber where the deposition happens, and then comes out from the back. And graphene is deposited on the top of the reactor. And so if we just look at the throughput, and these are data of about 3 years ago. So a BM303, now also the BM system is discontinued. There is a new one called CCS2D that we are also installing in the University of Cambridge, and I will discuss about it later. This can produce 1,000 or 2,000 square meters of graphene a year on wafer, while the Neutron can produce between 10 to 20,000 square meters of graphene a year on a substrate. So the production of graphene over a large area is not a problem anymore. The system works, and this company is just based a few miles off the engineering department. Also, the cost per square meter, again, this is about 2 years old or 3 years old data, but it's already well below the 100 euro per square meter range. Is about 60 to 50 euro per square meter in the production. And then with the future systems, it will go well below the 10 euro per square meter. So this is the production of film, and this is used for many applications that I will also discuss later. I will skip a movie showing the system. I want to discuss about this one. This is the new system that replaces the previous two. This also, of course, was developed over the years. The University of Cambridge and Einstein have always collaborated. And this is the newest system. It's called the CCS2D. It's MOCVD. In reality, it's a MO bracket CVD, so it can work as a chemical vapor deposition system or as a metal organic chemical vapor deposition system. And this is able to produce not just graphene, but also boron nitride and the transition metal cogenides all in the same system. And it can also produce multi-layers, layered structures. And I will discuss about this later in the talk if we have time. So I will also skip the movie about this, and I will go to the next topic. So the production of graphene as a film or layered material as a film is what I discussed until now. There is another approach which is called liquid phase exfoliation. And for many years, people applied this approach to carbon nanotubes. There were different groups, including the one of Werner Brau and Trinity College, who pioneered different ways of exfoliate carbon nanotubes when they came in bundles. And Johnny Coleman was a student of Werner Brau. Now he is the head of school of Trinity, of the School of Physics, decided that after some discussion to utilize graphite and a similar process to the one used for carbon nanotube to make exfoliation. So we also had experience on this. So Cambridge and Trinity College came together, and in 2008 we proposed a simple system to exfoliate graphite, which was to take it, throw it in some beaker with some solution, some water or something else, sonicate, and ideally get 100% monolayer graphene flakes. In reality, what we got in 2008 was 0.8%. So it was a very small yield, but was still bigger than 0. And so this paper was published. Jenny Hernandez was a PhD student at the time. Now she's a full professor. And strange enough, the title is high yield production or something, but the yield was extremely small. So it took a few years to develop a system that was able to achieve 100% yield, and is this high pressure homogenization system. I'm not going to go too much into the details of this. I can show you the movie here. So you throw the material on one end, it gets processed at a very high pressure in very small channels. This creates a very high shear that exfoliates the material. And once the material is exfoliated after one pass, it goes back into the other pass and keeps going on and on and on. And as I showed before, one system of this kind is very small. So this is about 1 meter times 1 meter times 1 meter. And this can produce thousands of liters a year. But most importantly, this process gets nearly 100% yield. So all the graphene that you put in is exfoliated. You don't throw anything away. While the process we developed in 2008, 99.2% of the graphite was thrown away. So again, this now gives rise to large-scale production and so on. So once we crack this, then this open up to different kind of applications. You can see printing. You have the ink, and then you can print on a substrate any patterns you like. So this was done for the first time in 2011. And after that, the field of inkjet printing, or flexo printing, or gravure, or whatever kind of printing of graphene, and of course, all the other related materials, boron nitride and so on, they were all printed. And this opens up the applications in flexible optoelectronics, RFIDs, energy storage, sensing, printed circuit board, and smart textiles. I have to say that we now have another interesting application on massive input-output antenna, MIMO antenna, that are used for 5G and future 6G application, all based on printing of graphene. But I will not have time today to cover this part, so it's not part of the presentation. So as one of the examples how easy it is, this is a printing of a circuit board. You simply put your ink, and then you do a screen printing system process that is the same that you use to print posters. And that's this is just a technician doing this in a shop that prints posters. And if you do that, you can get printed devices directly on paper, for example. So this is one of the examples, early examples done in collaboration with another Cambridge company called Novalia, another spin out of the university that does this with printed electronics. So you have the tracks, you have the sensors, everything on paper, and then you can put a picture of it, for example, of this musical instrument, and then you can play it. So it's a paper with ink on the top of it, and that there is a sensor, and then you can print. So that's the beauty of liquid phase exfoliated graphene. It can be used for cheap and wearable and flexible electronics. Going forward, 2D printing was evolved in 3D printing. So we can now extrude and 3D print filaments. I will not go into the details. But you can imagine how to do it. So you create a composite, and then you put it in an extruder, and then you can use injection molding. You can do all sorts of things. And within the graphene flagship, polymer composites have become quite important, and there are many companies working on it. I just cite a couple of them. For example, Avanzar in Spain, they opened this new plant that is 30,000 square meters to deal with graphene polymer composites. In the UK, we founded a company called Cambridge Graphene. This was fully acquired by Versarion, and now Versarion already by 2009 was doing multi-ton production of graphene inks. In fact, one of the products is called Graphenes and is based on this original formulation. And this is already being used in different applications, for example, on the skeleton for the Winter Olympic Games, on headphones, on it's been tested for interaction with airplanes as a strain sensor, and so on and so forth. So many other applications have been developed. I really go very quickly. Francesco Bonacorso was a postdoc in Cambridge, went to Italy and opened a very successful company called Bidimensional, and one of their first products was this motorcycle helmet that was very popular, and now the company is doing very well, and they are going in a variety of different directions using these inks. There is also, as I mentioned, a lot of work going on in the flagship on polymer composites. For example, this was one of the first prototypes of a drone that was using different parts on the wings and on the propellers made with the graphene polymer composite. This was spearheaded by Adel at the University of Manchester. And then again, within the graphene flagship, we have a large project going on with Airbus to look at the leading edge of the A350 for de-icing application, but also for electromagnetic shielding if there are adverse conditions in the sky. And this work has been going on very successfully. I just met Airbus very recently. Airbus is very keen on this, and it's going to continue and in a variety of different directions for the aerospace. Another area I want to discuss briefly is the area of space. There is a lot of options for the application of graphene and related materials in space, and we have a lot of projects going on, in particular with the European Space Agency, spearheaded by the University of Brussels, the Free University of Brussels, who are the sort of space champions for the graphene flagship, and with the company Leonardo in Italy. There are many examples. I will go very quickly through one. This is the first one is this heat pipe that it's used in the satellites to remove the heat from one side of the satellite and bring it to the sink. It works based on a simple principle. You have a porous wick that creates a capillary pressure that pushes around the vapor, and the vapor condensates and becomes a liquid and then goes through the wick, and so on and so forth. Why do you need this kind of pump? Because if you have a pump made with moving parts on a satellite, as you are all familiar with plumbing in your own house, heaters, they always break, and you always need to service them. So you want to be able to move water or liquid or fluids without, it's not, of course, they not use water, without having any mechanical wear and tear. So this is a very interesting application, and we have worked on it for a while, and we are still working on it with Leonardo. But the use of graphene increases the wettability, so reduces the startup time, because these pumps, because they don't have any mechanical parts, don't have a switch to be turned on and off. They turn off automatically when one side is hot and one side is cold. And so you need to make sure that they actually function immediately. And there's been several problems in satellites where they were down for months at a time because they were not working. So the increased wettability really reduces startup time. The layering creates a preferred liquid stream, and the increased wet thermal conductivity helps transfer the heat from the source outside the shell to the capital inlet core. And also it does reduce the size of the pores, which again results in increased capillary pressure. So this was prototypes were created. This is a very, very early prototype of a few years ago. Now, I don't have time to go in the most recent one, but this was tested in zero gravity experiments. You can see here me in zero gravity. So this is I don't know if you have ever done this sort of experience yourself, but it's quite interesting. And of course, I'm just wasting time while people are actually doing the experiments in the rest of the plane. So it's actually quite interesting, and this is not just for fun, but is necessary for the validation of the system before it's used in satellites. Something else that we are doing is using rockets We launched a rocket a couple of years ago called the Maser 14. We have another launch on the 22nd of November this year. So the way these rockets work is that they are divided in different experiments, and one of them is this ARLS experiment, the one that we did in collaboration with ULB. And this is actually an experiment to print graphene in zero gravity. The idea is that if you are going for long interstellar travels, you can either stuff your spacecraft with a lot of spare parts, or maybe in a very optimistic view, you are able to bring graphene inks or other kind of inks that then you can print to make your capacitors or sensors or whatever breaks down. The problem is, as you know very well, that printing requires gravity. So it's not very easy to print at 0G. So many attempts are being made, and this was the first one we did, and it went quite well. These are some pictures. The launch site is in the Arctic Circle. It's in the north of Sweden, and this is the base of the rocket. And then this was launched, and this was actually 3 in the morning, even though there is sun, because the sun never goes down in the summer there. And now is going to be different. So that's the launch of the rocket. You have a camera attached to it, so the rocket goes up into space, and then it's the second stage separates in order to stabilize the flight, as you will see shortly. And then you are able to access several minutes. You will see the second stage is gone, and now it's perfectly still. So now the experiment can start, and this works for up to 11 minutes, and then the rocket comes back to Earth, and you recover the samples. Something else we are doing, and is going to happen in the next few weeks. The date is not fully set. We are launching this rover to the moon. So this will be a lunar mission, which is part of the Emirates lunar mission. This is a collaboration with Fraunhofer, with MIT, with ULB and other universities, and of course the Rashid Space Center in Dubai. And this rover will carry a set of experiments on the wheels of the rover, and in particular, a set of different graphene polymer composites that will be studied by different sensors and spectroscopic techniques that are mounted on the top. And they are going to be able to look at the wheels of the rover for the interaction with the lunar soil. This is called regolith, and the regolith is particularly nasty because it sticks everywhere. But as you know, there is a plan to bring people to build a habitat, a human habitat on the moon. In principle, you have seen the Artemis launch has been delayed, but it will be delayed a few years, but it's going to happen. So there is a next manned mission happening and the habitat being built. So it's very important to understand the interaction of the lunar surface with different types of composites that will be used to build these systems. So we are going to look at wear and tear and other kind of properties. Of course, if the rover makes it to the moon and if it doesn't explode upon launch, or especially when it's landing on the moon. These are only 2 examples, but there are so many others that I cannot cover. For example, there is a large project that we are also involved with on wound healing in space, because when you cut yourself and in zero gravity, it's not very easy to heal. The gravity is very important to heal people. And then there are loads of experiments on optical communication that I will not discuss. We also have an option to bring these experiments to the International Space Station, and we're working on it. And the problem is that they have to be made extremely small. You only have a very small cube of space available. And then, of course, you need to work with an astronaut that need to be trained in order to run the experiment on the space station. So now let me change gear, and I really want to change completely topic, and still within the layered materials, and discussing about what is happening in the wider evolution of industry. We are all familiar with the first and second industrial revolutions, but what is happening now is what people are calling the 5th industrial revolution, or what they're calling industry X.0. So unlike what people thought about the IoT in industry X.0 on the fifth industrial revolution, the artificial intelligence is an integral part of the system. So there is a cyber physical cognitive system that is being created. And this, of course, gives a lot of advantages, but there are lots of constraints. And there are two actions here, one on the system, on the software, and so on. We don't really work on that. But the other action is on the hardware. So there are huge constraints in terms of data exchange, and especially in power consumption. And we really need to find a way of producing devices that can deal with data at extremely low power consumption. So graphene is ideal for optical communication because it doesn't have any bandgap. So it works at any wavelength, any frequency we want. And the optical absorption in the simplest approach is basically as shown here. If you have a piece of graphene that is doped to a certain level, if your energy of light is larger than the doping level, or the twice the doping level, you are able to excite an electron hole pair, so the light is absorbed. If it's not, you are not able to excite. And this would be the basic principle of light modulation. However, what's important to notice is that in real graphene, not ideal graphene, there are lots of processes that create these intra-band transitions, no matter what wavelength you have. And this is mostly due to defects and wrinkles and this sort of things. So ideally, we will go from each piece of graphene absorbs 2.3%. You will go exactly to 0, but you don't because of this intra-band transition. I will not discuss today what happens at extremely long wavelength, extremely low energy. So this is just about the only equation I'm going to show. And this describes the optical properties of graphene. There are lots of terms, but in reality, all of them are well known. There's the Fermi level here, there's the temperature, there is, of course, the energy we are looking at. But the most important term here for the intraband part is this tau, is the scattering time. The scattering time is the only true definition of quality of a film of graphene. And this is directly related to the mobility. So the mobility is related to the scattering time and to the Fermi level by this very simple formula, which basically tells you that the scattering time of 10, 100, 300 femtosecond corresponds to a mobility of 200, 2000, 6000, okay? So these are sort of basic principles to judge how good a piece of graphene is. 200 mobility or 10 femtosecond is a crappy piece of graphene. 100 mobility, 2000 is a normal piece of graphene. 6000 or above is a very good piece of graphene, and is what people are trying to do now, not at 0 Kelvin, at room temperature over a large area. And you can see why this is important, because while the real part doesn't depend of the electric constant doesn't depend too much on the quality of graphene, the imaginary part, which is the one that rules really the absorption and modulation, has a huge dependence. Now, I don't want to go too much into the details, but I just want to say that a graphene modulator is one of the simplest devices you can think of. It's simply 2 layers of graphene on top of a waveguide. This behaves as a capacitor. When you charge the capacitors, the charge accumulates on the top of the waveguide, and this changes the absorption and the effective index of the waveguide. When the capacitor is charged, the waveguide is transparent and no extra loss is added. So graphene is an ideal candidate for the loss reduction. Unlike silicon-based devices, they waste energy when they are in the on state, in the off state, and in the transition. Graphene only uses energy in the transition. So doing on and off, there is no energy consumption. This is very important for the future of communication. So if we now compare the traditional silicon photonics with the graphene plus silicon photonics, I'm not here telling you graphene will kill silicon, throw silicon in the bin and so on. No, graphene is marrying silicon. And this marriage of the two materials is what is creating our future. because in silicon photonics, we have an active photonic circuit, while in the case of graphene, is completely passive because the work is done by graphene. In the silicon photonics, we have the free carrier losses. We don't have them in the case of graphene because you don't need the free carriers. Graphene does the work. We have, as I mentioned before, a static power consumption. So a silicon-based photonic devices consumes power all the time. In graphene, we don't. And so we need implantation and other tricks in order to detect light because silicon is not a very good light detector and in graphene not. So there are really clear advantages. And then graphene is compatible with different platforms now because if I don't need doped silicon anymore, I can deal with silicon nitride, with glass, with polymers, and so on. And so if we look at the requirements for the future, we need to massively reduce the cost per gigabit of data transmitted. We need to massively increase the speed. We need to massively increase the capacity. But most importantly, we really need to reduce the power consumption. Most people are not aware that this little seminar that I'm giving or lecture will create between 300 and 500 grams of CO2, or even more, according to how many people are listening to this Zoom call. When you send a message by email with a big attachment, you create 50 grams of CO2. At this time, this present time, after the COVID pandemic, when everybody started using Zoom and so on, the greenhouse contribution of the data communication and ICT is bigger already of the one of planes. You know, everybody is concerned about planes, about private jets and so on. But by 2040, the influence of data communication on the global emission will be 3 to 4 times bigger than the one of planes. So when you watch your Netflix movie at the evening, remember this is not some, you know, very ecological and energy-free activity. And when you use Facebook, remember that the servers are in California. So you are in Greece or in the UK or in Italy, you access your Facebook, the query is sent to California and comes back. There's a massive wastage that goes on in most of these. Not to speak about the Bitcoins, that they are an abomination, because to mine a Bitcoin, you need a ginormous amount of energy and they should actually be banned. So when it comes to graphene, thanks to these properties, now the target, nowadays, the consumption is about 17 picojoule per bit. That seems a very small number, but if you consider the amount of, think about a movie, how many bits a movie is, and then we need to reduce it by at least 75% to less than 4, and that's what graphene can do. The other important point about graphene for photonics is that apart from many low cost and so on and so forth, but the most important property, it is wavelength agnostic. So thanks to the Dirac cones, the graphene is the only material that works at any wavelength. It means that with the same piece of graphene, you can have multiple wavelengths, multiple lights going at the same time. So now I will really go very quick for the next 3 or 4 minutes because I don't want to go into the details. I just want to show you some snapshot examples of devices that have been made. So as I mentioned, we have the modulator and the photodetector. That's the basic device, modulator device. The simplest idea is only one. I said 2 before, but the even simpler idea is just put a piece of graphene on the top of silicon. This works, but the problem is that the single layer of graphene doesn't shield you from the silicon losses, so the quality of graphene is almost irrelevant. So that's why we are using this term, double single layer graphene, which seems a weird term. Why don't we call it double layer graphene? It's not a double layer because there are 2 individual layers of graphene separated by a dielectric. And if you do that, you can get rid of the silicon influence and then really get a massive improvement in properties if you have a very high quality graphene. So let's go to some examples. This was the first phase modulator that we published in 2018. And V pi L is basically a figure of merit, and just trust me, 280 is a very good number in this field. This stuff was working at 10 gigabit per second, and we demonstrated 20-kilometer transmission in 2018. Things have improved afterwards. It was possible to do transmission of 10 gigabit per second over 100 kilometers. This led to the demonstrator that was taken at the Mobile World Congress, made by CNIT, Ericsson, IMEC, Nokia, and so on. A variety of other demonstrators were made, for example, on silicon nitride, working at 25 gigabit, on silicon on insulator, working at 29 gigahertz, and a pure phase shifter was created. As I said, I just went very quickly. Each of those examples, I could give a talk, but just ask me, it's now is really taking off this field. And last year, as a proof of principle, together with CNIT and IIT, where we're able to produce 12,000 modulators on a wafer. So this is 12,000 modulator on a 6-inch wafer. This is really a proof that the technology is working. And you can actually, maybe you cannot distinguish it in the screen, but there are some patches that are slightly darker, and those are the individual graphene flakes that are all distributed over this very large modulator. In fact, we are now, the University of Cambridge and Cornerstone just received from the UK government a funding to create a pilot line in the UK. This will be called the Layered Material Research Foundry, and I will be the director of this from January next year, when we are going to start. And this is already some preliminary work. We have produced our first 8-inch wafer with multi-project wafer, and this is going to be available in about a year and a half for general use. People will be able to send design for us to make devices. The other important point is the photodetector. I will go even quicker now. Just trust me, it works. You can do it. We have done different designs, but let's just skip forward because I want to spend the last minute on something else. So to summarize, the modulators with graphene are much smaller. The switches do not consume static power consumption, and the detectors are broadband. Okay, how many minutes do I have left for the presentation?
You have 10 more minutes, sir.
Okay, so in the last few minutes, I will now do a further step. So I started from growth, liquid phase exfoliation, then I went on optics. Now I want to go on quantum. So we are now facing what is called the second quantum revolution. The first quantum revolution was, for example, exemplified by the use of collective quantum phenomena. So a laser is a coherent emission of photons, many photons together, and the same for the transistors with electrons. However, what people need to realize is that for the laser, this was realized thanks to ruby, thanks to a material. And for the transistor, the first one was in germanium, the one we have now is in silicon. So there is a key aspect, which is the material platform. So now, in the second quantum revolution, we are looking at individual quantum systems, individual electrons, photons, and atoms, and we also need new advanced materials for this. And my point is that layered materials, in this case, not based on graphene, but mostly in HBN and transition metal dichalcogenides, are ideal for quantum applications. So nowadays, quantum technologies are the coming together of devices that were designed with the first and with the second quantum revolution. And it's not just about quantum computing. For example, there is a big field that is called quantum biosensing, and this allows you to have extreme resolution targeting specific areas inside the cells by using NV centers in diamond. And also what people are working now on is the hyperpolarized MRI, the quantum MRI, that will massively increase the sensitivity. So quantum revolution is not just computers, quantum computing. And also an use of the coherency of the photons can be done in what is called the coherent Raman imaging, chemometric imaging, which is very important for biomedical application. So we'll spend the last few minutes on this chemometric imaging. It all goes back to graphene and goes back to the Dirac cone. That is the reason for the Nobel Prize. As I mentioned, when you pump a piece of graphene, you create a population of excited electron and holes, and the electrons, they stay excited for a certain period of time, typically up to, but in reality is about 20 to 30 femtoseconds, and then they start decaying. During this time, when they are excited, the next pulse cannot be excited as well because of Pauli blocking, and this generates a modulation of the incoming light. So let me skip this. And this has created, in 2009, we made our first graphene-based laser. So, and this has been used for a variety of applications in terms of wavelengths between infrared to long wave infrared and so on. So the way it works is actually very simple. These are 2008 slides. You just make a polymer graphene composite. As I explained before, you chop a piece of it and you insert it in a laser cavity. And this polymer graphene composite acts as what is called Saturable absorber and makes sure that you have laser pulses coming out. So this is the old video when our first packaged laser with graphene. And this was connected. You can see the laser pulses here after connected to a photodetector. But what is more interesting is this second movie, because by tuning this bandpass filter, I am able to get a continuous tuning of the emission, thanks to the Dirac cone. It works at every wavelength. And in fact, the limitation is not the graphene, is the optical fiber, the erbium doping. It's the gain of the erbium, it goes off after 30 nanometers. The piece of graphene will work at every wavelength. So this brought us to the next step, which is the development of coherent Raman spectroscopy. See, in spontaneous Raman spectroscopy, when you have a pump or your spontaneous Raman spectrum that is being measured, all the molecules are essentially vibrating independently. And that's what, you know, with your normal Raman, you take your measurements and that works perfectly well, but is a bit slow. In coherent Raman, the idea is to come with a pump and a Stokes at the same time, so two laser pulses at the same time, and you actually are able to excite a specific vibration. And if you do this, you do it coherently, which means you drive all the vibration in phase, and the signal becomes huge. So you have an enhancement of up to 10 to the 10 with the with respect to the standard Raman. To give you an example, you take a Raman spectrum of graphene, it may take you, a minute or so to get a proper Raman. With a coherent measurement, you can take a spectrum in 1 microsecond. So the entire spectrum will be taken in 1 microsecond, much, much quicker of what you have normally. So in order to exploit this, the best idea is to do it for medical applications. So if you are sick at the moment, if you have a tumor or not, you do a biopsy, and the biopsy are stained with some colorant, they're called dyes, and they change color according if you have tumor or not. And then the doctor, looking at the microscope, just by using the brain, the doctor uses the brain of the doctor, looks at it, and says, okay, that's a tumor, that's not a tumor, this part I don't know. And there are lots of issues in this way. So nowadays they're trying to support doctors by doing artificial intelligence software that can analyze the images, but still, this is purely an image. You're looking like a picture, like a drawing, and you say, okay, I think this is it and this is that. It gives you no chemical information. However, as we know, Raman gives you a full chemical information. So, and over the years, spontaneous Raman has been used quite extensively for tumor identification. However, as I said, it's very slow. So this can be used in a lab, but not in real time, for example, during a surgery. The idea here is to use graphene to make a coherent Raman microscope that can work really broadband, so creates high speed, and allows real-time classification of cells and tissues. So now this picture will not be an optical picture, will be a Raman map that you take very quickly. So each pixel corresponds to a spectrum, and that allows you to tell if the tissue is tumor or not, but not based on a judgment that you make, based on the chemistry, based on the chemical signature you see. So what we need to do is to go from spontaneous Raman that gives you a massive information content. Coherent Raman is very quick, but very low resolution. We need to get a sweet spot there. So long story short, the problem to do that is this laser system, this coherent laser system. Nowadays, they sell these kind of things. They cost €1 million, the system from Leica, and it requires a very complex laser system and very complex to use. You need to have postdocs and PhD students. Certainly, it cannot be taken in an hospital and put onto a patient for a measurement. So what we were trying to do a few years ago is to prove that the same piece of graphene will work at different wavelengths at the same time. So in order to do this, we had to make two lasers that had one leg in common. And in this common leg, we put the same one piece of graphene. And what happened, okay, both lasers worked, but what was seen was more interesting. Both of them, they became synchronized. As you see, the lasing is starting, and after a few passes, you see both lasers are completely synchronized. So that was not expected in the experiment, but this is key because this synchronized emission is what you need to create a coherent Raman microscope. So then now we can put all of it in a shoebox, literally this size, no optical table, nothing. And the huge system that can use now that costs €1 million can be made much, much cheaper, much smaller, much lighter. And this can now be used for Raman imaging. And for example, you see are really Raman maps, and they can distinguish healthy and tumor tissue. The first test is done on polymer beads, PMMA beads, and you can distinguish the two composition very easy. But actually, the real test is to take a real biopsy with cancer interface and so on, and then you take the coherent system, and you can get a label-free, no dye. Of course, because it's a Raman map, you can have the plot at different frequencies, and this is an ginormous amount of information for the medical doctor when they are trying to identify if you have cancer or not, and if there is a transition. It is still an image. If you look on the left, it looks similar, but it's completely different because it has the full spectrum of chemical information. So we also started a company on this area, which is called it's called Cambridge Raman Imaging. And this picture is a real picture, is not a made up, a mock-up. Is the first product of this Raman spectroscopy system that is very small, is barely bigger than a microscope. And this will be commercialized starting in March next year for research purposes and also for medical purposes. I think my time is up now, and I don't have time to go on to other quantum applications. So I will end the presentation by acknowledging the Graphene flagship, the quantum flagship, and the other funding, and in particular, the loads of people that have contributed to the different parts of this presentation. Thank you very much.
Thank you very much. And now my colleague, Dr. Kakavelakis, will moderate the questions. Thank you.
Thank you very much, Andrea, for the very interesting presentation and a lot of information you shared with us. So I would like now to give the floor to the audience for comments and questions. If you, Andrea, if you can stop sharing your presentation. Okay, so I see Konstantinos would like to ask a question.
Yes, thank you very much for this very informative and inspiring presentation. I have few questions, mainly from my ignorance. So I would like, my first question is like, how can you control in the laboratory the scattering time during the fabrication? How you can control it?
So this is the most important question for everybody at the time. And what people are trying to do is not, I mean, there are ways to control it after the fabrication, but you can only make it worse. So for example, you can irradiate your sample and this will decrease your scattering time. But during the growth, it's what everybody's trying to do by, and the most successful approach at the moment is by working on the catalyst. So people are working on the copper catalyst that is used for the CVD. They're doing different types of treatments of the catalyst, and that allows to grow a much better quality graphene. There are also steps that you are better quality means longer scattering time. And there are also steps that you need to take when you transfer your graphene from the growth chamber to the final substrate. And at the moment, the state of the art is between 6,000 and 10,000 mobility at room temperature at the wafer scale, which is basically enough to have devices that beat any commercially available silicon-based device at the moment.
Thank you. May I have one more question regarding the lasers, George? So I like very much, you know, the tunability that, of course, is based on the properties of single layer of graphene of your laser. But one of the most important things in lasers is not only the tunability, but the line width in order to be able to detect, you know, small details. So my question is, what is the spectral line width of these lasers?
So the spectral line width really depends on the pulse width, and on the pulse. On the speed. So the pulse width that you need in order to do Raman is 1 picosecond or below, which means that you are limited in spectral resolution to a few centimeters -1. So you will not be able to take a Raman spectrum with less than 10 centimeters -1 in this system. There are, of course, ways to work around this, but you need to reach a compromise, and that is the compromise that one has. So that's why I say that coherent Raman, if you want to know everything about a piece of graphene in terms of the amount of strain, doping disorder, and so on and so forth, you need to use a spontaneous Raman system. But for chemical imaging or biological imaging, because there is so much work already done in the past 50 years on identifying different chemical species, different molecules, and so on, the resolution that we have at the moment is enough for this. And people have then published, of course, as a principle, a variety of different lasers working at different, we have done a 20 or 30 femto, 26, I believe, femtosecond laser as the smallest pulse width a few years ago. But that is not very good when it comes to use it for Raman.
Thank you. And George, may I have one more? The last one. Thank you. I would like to ask you one question. So the system that you have performed, that it has the shoe size instead of the big laser system, is, as you mentioned, is like very appropriate using Raman to detect, you know, cancerous cells. So you're talking about skin cancers, or you can go using fibers to even, you know, deeper. And this is my first question. And the second one, it's very nice that using this system, you can detect the cancer. But if you couple it with the work of I4 Samuel with organic lasers, you can treat the cancers as well. So how can we couple these two technologies? Thank you. And this is my final one.
All the most important questions all at the time. So we just had a meeting yesterday of like 2 hours to discuss the first part. Of course, at the moment, we are limited to the skin and sub-skin because of the penetration depth. So if you want to go deeper, you need to do biopsies, but biopsies is what doctors do anyway. So if you have a liver cancer, they need to do a biopsy. However, we are now discussing the development of a system that could go very deep, but I don't have anything to show now. So there are some ideas, but I cannot show them today. When it comes to the second part, indeed, what you say could be feasible, but at the moment we are focusing on getting the system out to the hospitals and to the researchers. So it's going only to be doing the detection. And the key part is not just the hardware, but it is the software. We have a program to develop all the artificial. Remember that when you do these measurements, because they're not just optical pictures and it's like a map, we're talking about gigabytes of data that are collected. So they are called the hypercubes. So we need to develop an AI system that can look into that. And we have a project with the computer science department of Cambridge, where we are actually developing this in order to be incorporated in the software. And later on, of course, what you suggested can be extremely useful, but it's not something that we are developing in parallel. We need to get the system up and running and on the market next year, and then maybe in 2 or 3 years' time we look into that. On the other hand, the going deep is something we are already doing, but I don't have anything to show at the moment.
Thank you very much.
Thank you very much, Konstantinos, for the questions and Andrea for the answers. So we have another questions in the chat from Amor Farag, and the question is the following: why the liquid phase exfoliation shown firstly gave small yield graphene, while the machine gives 100% yield?
So the reason was that the initial exfoliation in 2008 was done with back sonicators and tip sonicators. And the energy that is delivered to the sample is first in a tip sonicator only very close to the tip. And second, the shear rate that you can achieve is extremely small. With the high pressure homogenization, due to the design of the channels where the graphite goes through, you can have increased by up to 5 orders of magnitude the shear on the graphite flakes. And that results in a much bigger yield than originally was developed. Another point that happened over the years is a better understanding of the chemistry, so there's better solvents. But that only changed the yield between 0.8 to a few percent. But to get to 100, you really need to get this new design of the system. So there's a bit of it that is due to the chemistry that brings you up a few percent. A bit of it that you can do, for example, if you use the shear mixer that Johnny Corman proposed in 2014, that was better. But again, the design of the shear mixer is not as efficient as the one of the high pressure homogenization or a jet miller, as they call it in bidimensional. So it's the same concept. And essentially the idea is that all the force is transmitted to the flake in this way, and you can exfoliate the flakes. And that's why the yield is improving.
Thank you very much for the question and the answer. Is there any other question from the audience?
If the others they don't have, I have one more.
Yes, please.
It was very nice, the two parallel tables that you saw, that you compared, silicon and graphene regarding, the optical properties, very clear. But for me, please, can you please elaborate why you still need silicon? Because you mentioned graphene and silicon, and in comparison, it's silicon and graphene. Why silicon and graphene together?
Exactly. So I am not advocating to replace silicon with graphene. That is nonsense for me. I am advocating to marry together silicon and graphene. And the reason is simple. Silicon photonics builds upon 60 years, or what is it, even 80 years of investment in electronics and so on. A foundry, when it comes to producing wafers, waveguide, modulators, edge, whatever, it's so advanced that and it works so perfectly well. So of course we need to make the light go from A to B, and the best way to do it is a photonic circuit. That has to be made with silicon, or nowadays people are using silicon nitride. There are other platforms like gallium arsenide. I mean, they can also be used. I mean, but the most popular is the silicon of insulator platform. We don't want to replace that platform, but graphene can exploit it in a passive manner. So the silicon insulator is totally passive. The role of the silicon is simply to guide the light from A to B. And that's it. The role of graphene is to modulate the light, detect the light, and do everything with the light. It's done by graphene. All the job is done by graphene. But the job of guiding the light is done by silicon, and that has to remain. Because I mean, making waveguides in graphene is possible, but it's not even useful, because graphene is too much, absorbs too much light anyway. So for this reason, you put the two things together and you get the best of both. And let me say in the final part, I didn't discuss when it comes to the quantum integration. That's what happens at the moment. For quantum application, you need single photon emitters and so on. And transition methodical cogenides and boron nitride are much better than graphene than that. But still, you need to stack them on the substrate. They are still to be stuck on the silicon, because the light, when it comes out, it has to go somewhere, and the silicon does the guiding.
Thank you.
Thank you for the question and the answer. Any other final question or comment? Actually, I have one, and Andrea, it is related to the cost of graphene. So you have demonstrated that the cost of graphene has significantly reduced, and I think this is related to the CVD graphene. And do you think the liquid phase exfoliated graphene that is significantly cheaper than the CVD one, do you think it can be used in this type of advanced systems or devices that you have demonstrated with the CVD graphene?
In fact, all the Raman, coherent Raman is done with liquid phase exfoliated graphene. So, and that is inserted in a polymer, but the polymer is there as a matrix, is not for mechanical purposes. It's just there to ensure that when you stick it between optical fibers, it guides light properly. So that is an application with liquid phase exfoliation works. The other one I didn't show, but it works very well, is for antennas. Screen printed graphene is very good for antennas, and we have some very good results. And of course, for sensors and so on and so forth. CVD graphene is actually, when it comes to solar, as you should know, you can use liquid phase exfoliated, but also CVD graphene in different ways according to the chemistry you do. I think the solar is the place where the two come together potentially in the same system, and they can have a similar consideration in terms of cost. However, when it comes to the other devices, like a modulator, the amount of graphene you use is so tiny that, in fact, the cost per se of the large wafer is irrelevant. However, you know, the cost per gigabit per second is also very small. It has to be below $1. So everything matters, the silicon matters. So you really need to have an extremely cheap device. And you are not going, there are examples of liquid phase based devices, but they are not, the reproducibility has to be perfect in that case. So for optoelectronic devices that have to be integrated, you need to really use CVD. Then there is the whole different field of wearable and flexible. If I want to make a wearable photodetector, then probably I can, if I can, I would be better off doing with the liquid phase exfoliated material.
Okay, thank you very much.
George,
yes.
If Professor Ferrari has time, can I make one more question, because he mentioned something about sensors?
For me, it's okay, yes.
So I would like to ask you regarding, if this is, you know, a reality, about chemical resistive sensors. I mean, they are very much based on the detection of the pollutant of your target by changing the conductivity. So you are measuring changes of the conductivity. I can understand because of the mobility, they are going to be very fast. But since, you know, they have no bandgap, this means they are going to be conductive continuously. So is it possible to apply graphene in this type of sensors?
In the case, exactly what you say, they work very well, but they work too well, okay? So the problem of sensors based on graphene is not the sensitivity, which is fantastic, is the ability to discriminate one molecule from the other. And that's where all the, what people have to do is to do different kind of functionalizations, different kind of tricks in order to do that. Because of course the sensitivity is huge, but the selectivity is the problem.
Yeah, thank you.
Thank you very much for the question and the answer. So I give back the floor to Konstantinos to close the session.
Thank you very much. It was it's a pleasure to listen Professor Ferrari of a very small part of his work. I hope that he will be able to come to join us in the close future, face to face, but also online to present more activities that he is doing. We will continue the Sci Cafe talks on Wednesday, I think, with some Nobel Prize related talks from Professor Kavoulakis and some people from SARI that they are going to speak about quantum computing. And next Friday, we're going to have Professor Kimakis to speak to us about graphene-based and not only solar cells. So I would like to thank all of you. I would like to thank again Professor Ferrari for his contribution, a great honor for our initiative in our university. I don't know if Professor Kimakis would like to say something because he's a close collaborator also with Professor Ferrari at this stage. And then we have to close the connection. So Manolis, if you would like.
Andrea with us, close collaborator and friend. So we're very happy that we work together for the last 10 years. We'll continue for the next 10. Okay,
exactly.
Thank you.
And I'm very happy to come and visit as soon as feasible, but not before the 16th of November.
Okay, all right.
Next year, we'll have the conference again.
Okay.
All right. Thank you, all of you.
Thank you.
See you next week. Bye. Thank you.
Bye.